Hey, I'm Taylor Coffin, and my presentation today is on the Rankine cycle experiment we did the week before spring break. And a little introduction: Rankine cycle is an ideal vapor cycle, basically used for power plants to produce power. It's got four main subsystems: the condenser, the pump, the boiler, and the turbine. And you can use the steam-generated power to produce electricity, which we did to power light bulbs. And this is the apparatus that was given in the lab manual. We went over this, the lead went over it pretty good on their presentation. And the objectives for this experiment were to calculate mass flow rate, the pump work input, the boiler heat input, condenser heat removed, turbine work produced, turbine efficiency, and the cycle efficiency, both ideal and the actual. And this is a TS diagram. You see from 1 to 2, this is across your pump, and this is where work is put in. 2 to 3 is constant pressure process through the boiler, where heat is input. 3 to 4 is across the turbine, where work is produced. And 4S is the isentropic pump or turbine. Q out is released across the condenser. I did my calculations and I found the mass flow rate to be 0.026 kilograms per second, and pump work input 17 watts, boiler heat in 68 kilowatts, condenser heat out 66 kilowatts, turbine work I found to be 2.09 kilowatts, turbine efficiency was about 16%, the actual cycle efficiency was about 3%, and the ideal cycle was about 19% efficient. We were asked to do an uncertainty analysis, and I wasn't sure if we were supposed to add them all together. That way I did them separate, one for the 4-degree temperature difference, one for the pressure difference. And for the temperature difference of adding 4 degrees Fahrenheit based off incorrect temperature readings, the workout of the turbine was found to be about 2.04 kilowatts. And then on the other side of that, with minus 4 degrees Fahrenheit, the work was found to be 1.91 kilowatts. And plus 5% difference in pressure readings. What I did for this was, since the gauges read 0, I assumed that it could be a little off, maybe read 1. So I just used 1 PSI gauge pressure for this, and I found the work to be 1.89 kilowatts, the plus 5% difference in pressure readings, and 2.01 kilowatts for minus 5. And for 10% change in the mass flow rate, I found the work to be 2.3 kilowatts, and on the low side, 1.88 kilowatts. For the actual cycle efficiency, based on the same uncertainties, I found it to be 3.3% efficient when adding 4 degrees to the temperatures, 3.2% efficient when subtracting 4 degrees from the temperatures, which isn't that much of a difference. And the pressure readings went from 3.47% to 3.42%. And then with a 10% difference in mass flow rate, it went from 3.07% to 3.06%. So the overall cycle efficiency seemed to have less effect on the uncertainty analysis than the work from the turbine bit. And calculated turbine power I had was 2.09 kilowatts, and the electric power we used, we found from the meter coming out of the generator was 615 watts. And based off this power from the turbine, we could power 83.6 light bulbs. And some references and